Okay. Let's get started. So we're trying to finish decision trees. We'll get to ensemble methods. We probably won't get to boosting today, but maybe we might be able to start back. Okay. Couple of quick administrative notes. So your homework, as you remember, is due soon. This is the last tally that I saw. So I asked the TA to at least upload an entry. So here we are. There's 3 people who are doing better. You always managed to stay up at the. You always managed to stay at the top.
I'm sorry for that.
Are there some?
I know later on something might happen, but I hope it doesn't.
There's some interesting implementation tricks that everybody else should know about.
Yes, I can tell it, but then everyone will have.
Okay, so Wednesday we'll
yeah, sure.
learn some more implementation tricks. But that's the general setup. Is Shwang here? I think so. 0.5 is chance. You may want to look at bugging your code. The area under should be at least better than 0.5. So as I mentioned over email, we'll continue the project presentations next month. Right? So your slides are already up on Scholar. We'll just use the same slides. So you just present based on what you had in your slides, so you don't give some people extra time. Okay. So we're talking about decision trees. We looked at last time. We actually couldn't do this. We did look at this video. But these things are actually implemented. They're shipped in products. There's a lot of commercial interest in trying to get decision trees. And one of the reasons why decision trees are often used in a lot of time-sensitive applications is because if you think about training a decision tree might be difficult, but once it's trained, evaluating a decision tree is fairly efficient because there's a path in the tree and each node only requires you to look at a particular feature. So you have one feature vector, you just sort of pick dimension I, check against a value that tells you whether to go right or left, and you sort of follow this path down. So these are extremely cheap operations that can be made quite fast. That's one of the reasons why Kinect, for example, uses a decision tree. It doesn't use a single decision tree, it actually uses multiple decision trees for random forest, and we'll talk about that. That's one of those reasons that training these things may take a lot of time, but testing them is really fast because you're looking at sparse feature evaluations. Okay, so we talked about a couple of these things. We were looking at a running example of our data set, which was predicting miles per gallon, whether that's good or bad for a whole bunch of cars. And we talked about what a decision stump is, and that consists of a single variable and partitioning your data along that single variable. So every single setting that the single variable can take, you just, these were all your examples before partitioning, and these are all the examples after partitioning. So this is condition your data set on this setting, there is no sample mix, and condition your data set on this setting, a small number of samples that make it, right? And these things are indicating distributions after this condition. So think of this as probability of y given x cylinder equals 6. And we talked about how that's a stump, and ultimately you can make an entire tree. We talked about a few things that not all features attributes will need to appear in the tree. In fact, this is one of the reasons why the fact that not all features appear tells you that the trees can often be quite shallow, and you will never need to look at. So you could extract tens of thousands of quantities about a data point, but never actually use them in testing. Right? Because at training time, in some sense, you have done feature selection simultaneously with training. If a variable never appears in the tree, then it's not very useful. We talked about multiple attributes, that a feature may appear in multiple branches, but on a path, they may not appear more than once. That's the consequence of conditioning. The key problem for us is going to be that many trees will represent the same concept, but not all of them will have the same size. We looked at an example of this last time, and in fact, this problem is not just, this is NP-hard. We cannot find the tree that represents the same concept of the smallest depth, for example. That's going to be NP-hard. And what we said last time is we'll resort to a greedy heuristic. It's fairly natural and simple. You start with an empty tree, you find one really one best attribute that you should, or feature that you should split on, and you go ahead and split on that and basically recurse on each of the dimensions, right? So if this is your decision stump, you've decided to, your task was to find which attribute, or which feature, here you've chosen cylinder, then you've basically created your data set, you're splitting it up into various bins and feeding them recursively to each of these subtrees. So you're building subtree number 1 here on this data set, subtree number 2 here on this data set, 3 and 4. And ultimately this recursion goes on till some point and you get a decision tree. We talked about how you essentially need to specify 2 things. One is when do you stop and what criteria do you use to pick a feature. What criteria we had sort of nailed down with this idea of information gain and mutual information. The fact that we'd use this data set, we told you, look, the entropy in this data set before doing anything, the distribution over y is nearly uniform. It's not exactly uniform, it's 5 by 8 and 3 by 8, but it's nearly uniform. But if I split it on x1, when x1 is true, so all 4 of these cases, y is always true as well. So on that side of the tree, the entropy is 0. And when x1 is false, this entropy is fairly low as well. Right? There's only one sample of true and a whole bunch of false. This is a nearly deterministic distribution of that side as well. And that intuition we formalized as measuring conditional entropy. So split on a particular variable, measure the entropy of in y given x, and use entropy for that. And we talked about mutual information being the difference in entropy before splitting and after splitting. Right? So what was my uncertainty in this variable before I split and after? And even though I wrote my equation like this, it's clear that as the algorithm is continuing, because it's a recursive algorithm, what you're really computing is y given x so far minus y given x so far plus that extra part. Right? This is at the start of the algorithm, but at any given intermediate point, your data set is already conditioned on some number of things, right? Because you're already somewhere in the recursion. That makes sense? Okay. And so that was it. This was a really simple algorithm. You just find the feature that gives you the largest information gain, or has the largest mutual information, which is the smallest entropy left in y after conditioning. Right? And we looked at this visually. We talked about here's one variable that has these states, and for each of these states, looks like the distribution on y is pretty deterministic. The entropies are low, and therefore mutual information gain or mutual information is high. And if you have some things that have high entropy left after splitting, then the information gain. So you would not split on this first. Okay, and we were talking about when do we stop last time. So there was one base case which was pretty simple. For example, if you already nailed down the entropy to 0, this is a fully deterministic distribution, there's no more entropy left, conditioning will not reduce the entropy any further. The other base case was when you have made your way down the tree to the full depth, that every single feature has been conditioned on, there's no more that you can, this is just basic. The third thing that was suggested, which didn't turn out to be true, was if all features have 0 mutual information or information gain. And the counter example that we showed you last time was the XOR counter example. The idea was, here's an output function, here are 2 inputs. It's a deterministic mapping. If you look at the distribution of y before splitting, it's a 50-50 split. Let's go ahead and split on a equals 0, right? So every time a equals 0, there's still a 50-50 split in y. That's what this is indicating. A equals 1, still a 50-50 split in y. And if you just repeat for b and b equals 0, b equals 1. And what that tells you is that right now, since this entropy is the same as this entropy, the mutual information is 0. There's nothing we gain from splitting on that. And therefore, our algorithm says just stop, don't do anything. There's no feature that can be done, so they would just stop right here. And you would end up predicting, at this point, because you haven't split, all you can do is look at probability of y and just make a guess, one way or another. But you can actually get perfect classification, at least on this toy data set, by going to level 2. Right? And the reason here was that because we're measuring mutual information one at a time. So we're always measuring sort of the mutual information between y So actually what we're measuring is x1 through xd minus 1 so far, things that we have entropy of y given x so far minus entropy of y given x so far, comma this new xi. Right, this is every time that's the, you're sort of taking an argmax over I of this. Right, the one single feature that gives you the most information gain based on everything that I've seen so far plus this new feature. Because you're doing this one at a time, you can't tell when a feature by itself is not good, but when combined with the few others actually does result in good. Does that make sense? And this idea can actually be generalized to the parity function, right? So I can have x1 or with x2 or with xd. Right? So I can think of this as just, this is a y that's just counting the parities in all the x's. Is there an even number of bits that are on, or is there an odd number of bits that are on? And you would still end up with this problem that any particular dimension that you check still seems 50-50. You just can't make any progress. But that function, the parity function, is actually representable just like the XOR is representable. You just have to go full depth. As soon as you go level D and condition on everything, that's when it becomes deterministic. Anything before that, it still seems 50. Does that make sense? Okay. And this idea of the fact that there is a model in our model class that can represent the function that we're trying to learn, but we will never reach it, is the idea of optimization error that we had talked about. If you remember this figure that we talked about, that there was some modeling error, so there was a model class, in this case decision trees on D variables, right, of some depth. Our modeling error is actually 0 for this particular function if we're trying to learn, right? Because that does lie in our model class. The error that we're making is optimization error. Even if we had infinite data, we would never find it because we cannot perform the search for the best decision tree. That's NPR, and we're using a heuristic, which is a greedy output. Does that make sense? Okay. Let's see if there's anything else here. Okay. So I think so this is sort of the, if you had to give a pseudocode for what to implement, here's what a decision tree sort of pseudocode roughly looks like. Here's build tree with this data set and a particular output that's given to you. And if all output values are the same in the data set, then just return a leaf node that says predict, right? At this point, there is no more entropy left in this output variable. At this point, you just predict the majority or the only unique output. If all input values are the same, then you can't do anything better. Right? At this point, all the input values, all features are identical, so this is base error. So these are the two base cases that you check first. Otherwise, you find the attribute X with the highest information gain or mutual information, and then you basically split. If it has X distinct values, then you create that many leaf nodes and you basically call yourself. So that's essentially the pseudocode for any implementation of decision trees that you have to work with. Yes?
I was wondering, for the example with the cars, we have different number of cylinders. So like if you're splitting on that variable, you have a different branch for each number of cylinders. But like, could you also do less, like only have 2 branches, like maybe have less than 2
Yeah.
cylinders?
So far we've been talking about discrete variables, features that have some discrete number of settings. As soon as you go to counting type variables or continuous variables that may potentially have infinitely many states, we just can't branch it that way. So we'll have to think about sort of clipping the possible output space into greater than the threshold, less than the threshold. Yeah, and we'll talk about that in a few slides. Any questions about this? Yes.
So is there a solution for this problem?
Is there a solution for this problem? No. The only solution is you have to go. So this, for example, pseudocode does not stop when it hits 0 information gain or 0 mutual information. It just keeps going. And what you have to do is go to depth D, which is the number of features, and then we'll talk about in a couple of seconds. You may actually prune back, but You want to go, if you go all the way till depth, so you can at least represent this. But in a lot of cases, you'll be overfitting. We talk about that. Okay, so that's actually a good starting point for that conversation. Decision trees will overfit, one of the reasons why decision trees will overfit is if you compare decision trees to all the other algorithms that we learned so far, SVMs or naive Bayes or logistic regression, any of those, we always talked about priors. What do you believe before you see any data, right? And the role of our priors were to sort of nudge the classifier towards simple classifiers, right? To give you an output which was just predict the mean of the data set if this is a regression problem, or if it's a classification problem, nudge you to predict. 2+ classification, just predict half and half probability. So logistic regression with a 0 weight will give you probability half and half for every single data point. Like there is no such prior concept here if you think about it. Nothing is asking you to give you a simple output, right? So if you think about this, when you learn a decision tree like that, if you end up, you can always, so if there is no noise in your data set, if you condition on every single variable, at some point you can always drive down, if there's no label noise, you can always drive down the uncertainty to 0, right? It may just end up being that the number of instances in that bucket is only 1. So there's only one sample that has passed all these checks and reached here, and therefore the uncertainty here is 0. But you can always do that if there is no label noise. And so decision trees try very quickly partition the feature space into extremely small bins, and there they will have low uncertainty. And so that's why there's a good chance that they will overfit. Right? So you can always drive down training error to 0 if there is no label noise. If you don't have an exact same identical set of features labeled with class 0 and class 1, you can always drive down training error to 0 by making the bucket small enough. So this is another one of those things where you're going to have low bias, high variance classifiers. Right? These are overfitting classifiers, and therefore what we have to do is we have to somehow add some bias towards simpler trees. And so there are different definitions of simpler trees that we can come up with. We can come up with sort of shallower trees, so trees that have some small level of depth, which means they cannot check too many features. You can check. So each time you check something and branch, check something else and branch, if I put a threshold on the depth that you can possibly go to, right, then you can at most check D features out of the total M features out of the total D that you may have. Right? So you can bias yourself to some small depth, or you can have a fixed number of leaves, so I'll allow you to go as deep as possible, but you can have lopsided trees. So one path can be really long, but the total number of leaves is small. Or something smarter, which is use statistical tests, which we won't talk about. But you can also, like sometimes before branching, you check whether this is statistically significant. In general, in a lot of cases, this is sort of the cartoonish figure that we've drawn a few times on this slide. Right? On the x-axis will be some measure of model capacity or effort or learning effort of some kind. In this case, it's tree depth. So as you increase the depth of your decision trees, your training error will always go down. But you'll find at some point is that your validation error will stop going down, and at some point you're overfitting. So you'll see these sort of curves. And in fact, that's a good measure to sort of keep. That's often when you want to stop in some sense. But we'll talk about one way of stopping. So how do you reduce overfitting? One of the really good ways is because we talked about, let's say you want to prefer shallower trees, but at the same time we don't want to stop anytime we first hit that depth, right? Because even though the information gain has gone to 0, you do want to continue growing your tree to a deeper level, because at some point the function may become deterministic. Right? There may be multiple features that combine together to give you some gain. So you don't want to stop the first time you hit that depth. So a common strategy is to sort of grow your trees, because it's a recursive function, to grow your trees all the way till some stopping criteria, which is either that the entropy really has gone down to zero, the two base cases that we talked about, zero entropy, or you have, there's just label noise, there's no more features to be checked. So you grow your tree out to the whole thing, and then you prune back from this stage to the desired depth. The way this pruning is done is you basically measure performance on a separate validation set. So what you do is you sort of create a really deep tree, and then you visit every single leaf at this depth, and the internal nodes, and you checked about if I collapsed these two into this leaf, right? Does that improve my performance on a validation set? So you sort of on training you grow to full trees, and on validation you come back. I'll show you a demo of that. Okay, so here's a particular data set. It contains basketball matches of some team, right? So here's the outcome, whether they won or lost, and here are all the discrete features. Where was it played, home or away, what time, some person named Fred, did he start or not, some other person, what position were they playing, and whether the opening center was tall or short, right? So there's some discrete features that you're working with. We're not going to do any pruning initially, and we're going to say the splitting function should be information gain, and I'll say, okay, run this algorithm, and so here's sort of the decision tree that it learns out, right? If the game was played at 9 p.m., they're always going to lose. And then, frankly, they always lose at 9 p.m. If the game is played at 5, and their defensive player, Joe, if he plays center, then they lose. If he plays forward, then they win, right, so on. And this thing right here is node accuracy. So what is the entropy, if you will, or how certain are we at the nodes? And so the red is 100%, right? So all the leaf nodes here are completely certain, right? You sort of gone ahead, and this is a small data set, and so you had to check very few things. And so this path is checking 1, 2, 3, 4 things, and then you're sort of out to 100% accuracy, right? 100% training accuracy. So you can check where was the game played, whatever. Here's something else that, this is the pruning thing that we talked about. So I'm not quite sure what they mean by pessimistic pruning, but I think it's the same sort of ideas. If I run, so if I initialize and run again, it was too fast, but all that happened was that this subtree was collapsed. So it actually it created a full tree, and then it sort of pruned that tree up. And this thing is now yellow. What has happened is that 19 of the 20 training examples are now correctly classified. Before it was 100% correctly classified. So even though you had sort of built a tree that was giving you perfect training accuracy, you found that on a validation data set, pruning this back up to this leaf actually improves performance. Right? So even though this has less node accuracy, this is a better tree. You're going to have better generalization. Right? So there are sort of things that you end up learning out of.
Is it the validation data set? That is the entire training data set?
I think there's a split that we're doing. There's some split that they're using. Pretty random. I think they're using like a 50% split. So, but you have to go to a new data set, because if you continue sticking on that old data set, obviously you sort of nail down the training accuracy. Does that make sense? Any questions about this? Okay. So this should also sort of tell you, this is another example of the thing that I was mentioning last time, that this is one of the reasons why people in biology or other fields tend to like decision trees a lot, because you can sort of read off the rules that the decision tree has learned if you have semantic features. So every feature has a name and not something that is obscure that you're measuring, then you can sort of convert them to. So in general, you're going to have sort of this sort of curve that if you don't prune, you'll do worse. If you do prune, so this is accuracy on training. So this is the size of the trees. So as the size of the trees increases, your training accuracy only goes up. If you don't prune, then this is your accuracy. If you do prune, then this is your accuracy, right? So you do better after pruning. The other thing that is commonly done is to convert a tree into an equivalent set of rules, and then to prune each rule independently. So, for example, as we've been looking, if your features have some semantic meaning, so for example, sunny, overcast, rain, whatever, you can convert these paths into logical formulas, right? You can say if outlook is sunny and humidity is high, which was outlook sunny, humidity high, then what I'm going to predict is always no, right? So Latent is no, whatever, right? So each of those paths you can write down as some logical formula. And so all possible paths you can write as a set of rules, and what you can do is you can just sort of check the validity of each rule on some validation data set. So you can independently prune each rule. What that will do is it means that if you end up throwing this rule away, but you end up keeping this rule, it's sort of halfway pruning, if you will. You're sort of, it's no longer corresponds to any particular tree, but it just corresponds to a set of rules. Does that make sense? Okay, so those are all heuristics for preventing overfitting in decision trees. Here are some other things that we need to talk about decision trees. So far, everything that we assumed was that you have discrete features, right? Because we needed to branch on the various state of the features. What if you have real valued outputs, or things that are in theory infinite valued, but practically just high branch factor values. So for example, model year. Yes, in theory infinitely many, but you're going to see cars made in 70, 77, 73, 74, 71, 78, right? So there's a high branching factor. What's going to happen is that in theory infinitely number of possible split values, you only have a finite data set. So you only have a finite number of relevant splits, but even if you branch on every single split, you're going to end up with these decision stumps, if you will, that in each bucket, because they have such a large branching factor, they're going to, everything, even if the data is uniformly distributed, you're going to divide your data very quickly. Right? So if this is 100, suddenly now your data set in each of these buckets is 100. Okay? The other thing that is going to happen is when you have variables like these that have extremely large state spaces, information gain is likely to pick them. Do people see why? So anytime you have a variable, let's say you have two variables in your system. One takes 2 values, one takes 100 values. Compute information gain due to that 2 state variable and a 100 state variable. What's going to happen is that the 100 state variable is most often going to lead to these extremely sparse distributions. And so information gain due to that one will be extremely high. And so you end up picking it extremely early. Does that make sense? So here's another way of thinking about it. So you have some data set x1 to xd. This is the data matrix n cross d. Each row is sort of, and this is car 1, car 2 all the way. And here's a common mistake that happens. Let's say there's ever an ID column which goes 1, 2, 3 all the way till n. And let's say that stays in your matrix and you feed that to a decision tree algorithm. What do you think it ends up doing? Zero, exactly. Because it says, oh, I'm extremely happy. ID is the first branching factor. ID equals ID equals 2, all the way till ID equals n. In each of these buckets, you have exactly one data point, right? So if this was a 2-class problem, if y is what we're trying to predict, it will have just exactly one value here and 0 here, right? So you end up with one value here and whatever. You end up with a bunch of sort of zero entropy distributions, take an average, you're done. Try to generalize, you will never, because none of these IDs will be seen again, right? And this is, even though this is sort of an extreme case of this, think about another variable. You have like a consumer database, and one thing might be like, the date of birth or credit card numbers. Those are extremely large state space variables, and they're going to they're going to shatter your data set into extremely small buckets. And they will seem like they have high information gain, but they don't actually have high information gain. Or they do, but for it's uncomparable. the information gained due to this is uncomparable with another variable which only has 2 states. Right? So what is often done is you don't just look at information gain, you look at information gain divided by some normalization constant, and either that normalization constant is the state space that we're taking, right? So if this is a 1,000-dimensional variable, this is a 2-state variable, you either divide by that, or another trick that is used is you look at the entropy in this column. Right? So if xi is the column that we're talking about, what is the entropy amongst all these branching factors? So if really you have a uniform distribution over 1,000 things, then you don't want that because that entropy will be really large. But if you actually do have a variable, which let's say it takes 1,000 states, but only 2 of them really happen. This one is ever seen in the data set, and this one is ever seen in the data set. The rest are just never seen in the data set. Right? So even though it has a large output state space, its entropy will be much smaller and be comparable to a 2-state variable. Does that make sense? So we often divide by h of xi. So information gain divided by entropy is often what is used to normalize these things.
Can you explain this part again?
So what I'm saying is, let's say you have 2 variables. One takes 2 states, the other takes 1,000 states. But if you think about the entropy of this variable with 1,000 states, it's possible for it to take 1,000 states, but in your data set, it usually just takes 2 states. Right? So if you compute the entropy of that, it'll be pi log pi, where I is the bin, right? So negative pi log pi. Everything else will be 0 log 0, 0 log 0. And so it'll be only these 2 states that matter. So even though it takes 1,000 states, it'll start looking comparable to a 2-state variable, which would not if you had naively divided by the number of states. Then you would reverse penalize and always end up picking the low state space variables. Does that make sense?
And in this case, I prune all of the unused values.
Yeah. So you would if you end up picking it, you will branch on this.
Or take only just these 2.
Exactly. Or you will let it go, but then in the pruning stage, most of those nodes will go away.
But if you don't say the state, why do you branch it? Why do you?
So if the data really is 0, then you're never going to, after branching, there's nothing to do with it. So if there is a bucket and there's no data set that comes here, then that's one of our base conditions. You will never recurse from here. There's nothing to do. But if it's not 0, if it's like I see one sample with state 1 and another sample with 0, this will exist for a while till you go to the pruning stage, in which case this might even go away in the pruning stage. Does that make sense? Yes?
So, like, what happens when you don't see that particular value in the training data, but you do see that in the test data?
Yeah, so this is a common thing. After you've employed pruning, if you've sort of removed certain nodes, then you can no longer go down those paths, right? So you sort of have to make the best. This is sort of embedded in some tree so far, right? So at that point, you have to just make a prediction based on here. You can no longer follow the path down any further.
And how do I make the predictions if I have only rules? I don't have the actual numbers.
Say that again. How do you make?
No, I make a decision if I can't go deeper in the tree based on how the numbers. If are 3, 1, I go with the first
Right.
class. But if I have only rules,
I see. If you have only
don't have
rules,
these numbers.
So I guess the question you're asking me is, I know the statistics at leaf variables, but I don't know the statistics at internal variables. Yeah. In that case, you would have to keep the statistics around. And one way of doing that is to just have a leaf variable underneath it and keep the statistics here, right? So you can't follow this down anymore, but if you remember the statistics, how many times did I see this in the data, what do you do? So these are sort of like outlier cases that you have to handle by saying always predict majority numbers. Make sense? Okay, so this was one way of handling, just sort of stepping back. So far we were talking about discrete features. Now we're talking about discrete features that may take a lot of values and that can shatter your data set, and so you want to handle that appropriately. But what about features that really are sort of continuous variable, right? So one way of handling that is by thresholding. This is sort of what Hunter suggested as well, right? So you don't try to branch on every single value because that's going to be hard. Let's just pick a threshold. And so each stump now is just going to be a binary sort of stump. So it's going to always look like xi, and it's either greater than or equal to some threshold, or it's less than some threshold. Okay, so xi less than threshold, xi greater than threshold. Okay, so those are the splits that you're going to see. And what you're going to have to do at training time, when you're sort of building your tree, so now our goals are twofold, right? We have to know which feature to pick, and we have to know what threshold to check it against. Right? So those are the two discrete and continuous parameters that we have to optimize. Which feature is discrete? Threshold is continuous. Right? So choosing the threshold, even though it feels continuous, you can make it discrete. One way of making it discrete is you realize that even though the actual threshold value, your variable is continuous, I'm only going to see a small number of settings of that, right? So actually, let me do this one. So here's the next one, XT. Here's the data matrix again. Let's say this is the continuous variable, and it has some values, 20.5, 22.3, blah, blah, blah. And let's say what I've done is I've sorted my data set so that these are always increasing now. Right? So 20.5, 22.3, 25.1, blah, 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 all the way to 30.7. There's some numbers, right? And what I've done is I've sorted the data set. Even though this variable is continuous, I only have n data points. And so when I care about these thresholds, there's only n plus 1 thresholds that could possibly make any changes to this data set. Right? So there's one threshold which is here, this is T1, everything greater than T1, everything less than T1. There's one threshold which is here, T2, everything greater than T2, less than T2, and so on, till Tn plus 1, right? There's only n plus 1 possible thresholds that can split your data one way or another on these cells. So even though this is a continuous variable, I just need to check the intervals between these quantities. Does that make sense? So this is a way of converting this continuous variable into a set of discrete thresholds that I need to check against. So I check T1, I check T2. When I split against T1, all the data will land here. Everything will be greater than T1. And so it will have some P of y given x I greater than equal to T1.
Which is the same as.
Right? Which is the same as P of y that I started. Right? And I can do this for T1, T2, T3, and it's going to have different sort of distributions on both sides. Does that make sense? And so all I have to do is check all possible of these thresholds for a continuous variable. And that tells me what is the best threshold, if you will. Does that make sense? So this is a way of converting a continuous variable, a continuous valued variable, into a whole bunch of discrete thresholds that you check against a binary classifier, a binary stub.
It might happen that in your validation set, the values are actually like all are beyond 30.7.
So in which case you would keep sending your data down this way. That's what. I mean, if the statistics of your training data don't match the statistics of your test data, all bets are off. Right? But if you see the same statistics, then you'll end up making the same sorts of guesses.
Would you sometimes want to do three-way split?
Yeah, so you can have multiple thresholds, right? T1, T2 at each vertex. You can sort of generalize these things. But it's not going to matter because, and I'll talk about this soon, as soon as you start having thresholds, you can check against that same feature multiple times, right? You can do x1 greater than T1 and x1 less than T2, right? So you can sort of have these various bins of the same thing. It's not worth having, your code will become slightly more complicated if you have M array splits on each. So this is what we're talking about. If x is real valued, you define information gain of y given x against that threshold. So you check, probability of x less than threshold, the conditional entropy, probability of x greater than threshold, the conditional entropy on the right side, and this is what you define as the information gain for this particular threshold, right? And what you basically do is, I'll stop after this slide. What you basically do is, now you have to pick both a threshold and a variable. So you define the max information gain over all possible thresholds for this variable, and you pick the variable with this max information again. Right? So what we're doing is, we are picking a variable which has, so the variable that we like is the one that has the best threshold within it possible. There are multiple thresholds that it can have. We check against all of those thresholds and we pick the one with the highest threshold. I'll just show one stop here. And I'll give you a break, but here's so let me do, this is a demo that we've seen before, but I'll construct a harder data set this time. So this is a decision tree. Here's class 1, here's class 2, right? So a whole bunch of data around it. And let's say classify. Right, so it ends up carving out this sort of a decision boundary, right? And if you ask it to generate a report, it'll sort of give you this sort of a thing. There's only two features, X and Y, which is first coordinate, second coordinate, and it's repeatedly splitting on both of them, right? So Y less than something and Y greater than something makes this prediction, and checks on Y again, and each one of those define one such decision, one such linear boundary, right? And so by checking against those features, you're sort of carving out these sort of wings and saying this is what's happening. Okay, let's take a minute here.
Tell me how to keep using broken.
I think
She's gushing.
I think it's not. No, this is.
I was like, oh my god. I was like,
Oh, you were talking.
You can run it on it?
I need the extra credit.
Can we rerun it with the don't prune? With the don't prune check?
No, that's
Oh, then to go to deeper.
well, what I did was I tried to see if I had like a better decision, but it was like showing that one generation. So I was running it and see if the C equals 10, C equals 20. Luckily, I have a laptop, so that's what I worked
Let's give you the really accurate. What about the estimation error?
That still exists. But even if you had infinite data, so even if how does infinite data affect you? It affects you because
So, I'm in it right now. I wasn't in it last year. Yeah, I did grew up staying
let's resume. So we're talking about decision trees with continuous variables. We talked about thresholds. That. The last thing we talk about is so far everything that we've said is for classification, right? But if you think about what we're talking about, it's all about creating splits. It's all about creating pockets of feature space, and then the only predictions that happen is at the leaves, right? So if you could create these splits and get to the leaves, at the leaves you can do whatever you want. Majority vote was doing classification. You could also do regression at the leaves, right? So this is a tree. We've come down to one leaf. At that leaf, we can just decide to predict, just the average of value of the data points that are assigned to this leaf. So for example, this is one leaf, right? So x greater than some threshold. This is leaf 1, this is leaf 2. It just takes the data points that are assigned to it, so this becomes a piecewise linear regression function. Right? You can do piecewise, this is piecewise constant, you can do piecewise linear, you can do piecewise polynomial, and intuitively, visually in your head, you should think of it as this sort of a setting, right? You have two features, x1, x2, and you're fitting a function which is you're fitting a different function in different pockets of the feature space, where the pockets of the feature space are being carved out by the decision tree. So the decision tree just says x1 less than this threshold, x2 less than this threshold, that's region 1. This is region 2, this is region 3, this is region 4. This is a top-down view of this. So these are the various regions in your feature space, and within this region, you can just predict the average value, or do a linear fit, or do a polynomial fit. Does that make sense? So just like there are classification trees, there are regression trees as well. And this idea has been generalized not just to classification and regression, but you can store in computer vision. People have started doing these things where you actually, the input is a patch and the output is a segmentation of that patch. So you're storing not just a single label, but all labels of all possible pixels which will be input to that. So you're storing an exponentially large output. But we haven't talked about that, so it's not very well. The other final thing to keep in mind is, in practice, a single decision tree will always overfit. And so what people often do are these things called decision forests or random forests. And what they'll do is they'll train multiple decision trees on different splits of the data. And that's something that we're going to next, which is this idea of bagging. So what you'll do is you'll train one decision tree, another decision tree, another decision tree. At the end, at test time, you have all of these. You're going to take your data, feed it through this. This is going to give you a prediction. Either it gives you a confidence value, or if it's a classification thing, it either gives you just a prediction or some confidence, and you average those confidences, and that's your final thing. Right? So this is also called an ensemble method, or a committee of classifiers, or basically bagging, which is yes?
Hey, you said that they'll overfit, but is that only if you don't prune them, or is that like?
Yeah, so pruning is one way of preventing overfitting. This is another orthogonal way of preventing overfitting. You can do both. You can prune and average, and you can combine all sorts of tricks. Okay. The thing that you lose with bootstrapping, the thing that you lose with this ensemble of methods is that now you're again back to a black box approach, right? Because you're not quite sure why you got that gain in performance. With a single tree, it was all interpretable. You follow a path and could give a rule. Now it's an average of 100,000 rules, and you're not quite sure what's going on. Okay, so at this point, we're done with decision trees, or sort of classification and regression trees. We need you to understand a few different things about them. That they're extremely interpretable, easy to implement. They might take a lot of training time, but at test time, typically if you only have one or a small number of trees, they're extremely fast to evaluate, which is one of the reasons why they're preferred by in a lot of applications. We need you to understand mutual information gain. Don't really worry about the subtleties between what is different between ID3 and a C4.5. We don't really care about that. We've sort of told you a general heuristic. The recursive algorithm, we need you to be familiar with that. They can be used for a bunch of other tasks, even though we just detail them for classification. And in practice, when you use decision trees, you need to understand that they will overfit, and you will need to use either an ensemble of decision trees or some sort of heuristics to keep the capacity in check. Okay? All right. So any questions about decision trees at this point? Okay. There are really nice toolboxes available for using these sort of things. Okay. The next topic that we're going to is called ensemble methods. There are going to be two methods that we'll look at. One of them is called bagging. That's the cutest, I guess, photo I could find of a cat in a bag. And that would actually boosting, which will make sense next time. Like that picture will make sense, I promise. Right now, it doesn't make much sense. But at a high level, you'll hear terms like ensemble methods, mixture of experts or committees. With boosting, you'll hear words like A to boost, L to boost, logic boost, and then there's going to be some your favorite keyword boost. Right? There's just like there was the kernel era, there was the boosting era, and there was a whole bunch of like I do this plus boost, and it was a good formula for a while. But anytime you hear that in your head, you should think about it's an ensemble approach, and there's two general kinds of ensemble approach, boosting being one of them. Okay. So before we talk about these ensemble approaches, let's take a look back. Because at this point, we're getting to finishing off supervised learning. We're getting close to that. And so it's often nice to sort of look back. We've sort of gone through regression methods, classification methods. You've looked at least squares, robust polynomial regression, robust least squares. For classification, we've looked at linear classifiers, naive Bayes, logistic, which, by the way, so if you got that wrong in the midterm, is logistic regression a linear classifier? Yes, it is. Linear SVMs, non-linear classifiers like decision trees, neural networks, k-nearest neighbors, right? So we've gone through, we went through this particular ordering. One of the reasons was that there was increasing complexity in some of these things. That you could, for example, kernel SVMs were contained in them a special case with linear SVMs, right, for a particular choice of the kernel. Decision trees contain in them, not decision trees, but neural networks contain in them as a special case a linear classifier if you don't use any hidden layers, right? So we're expanding the hypothesis fast. The thing to always keep in mind in any of these things is this was the most illustrative sort of reason why I go back to reason why I like this demo that I'd shown you guys was that we did this for polynomial regression, and back then this was sort of simple and it made a lot of sense, but there was some data, and we had said this is the best first order fit to this model, this is a regression problem, and we had asked for increasingly higher order fits to this model, right? So on the x-axis was complexity of the model class, and I was trying to sort of generalize this out. That as the complexity of the model class increases, your performance on training data will get better and better because you have nested model classes. And so you will have low bias if you're measuring bias as difference to this. But if you have another sampling of your data set, you will have high variance. The curve that this is learning to the curve that you will learn on a slightly different perturbation of the data set will be extremely different. And we talked about this in overfitting. This was regression. You can make similar arguments, nearly identical arguments for classification. Right? Think about a decision tree. It's going to, as you go deeper and deeper, you can get 100% training accuracy. But if I make a slight perturbation to the data set, the decision tree that you learn here and the decision tree that you learn here, if you're going all the way deep, are going to be very different. Right? So in general, there is going to be a dichotomy, or not a dichotomy, but a spectrum between more complex hypothesis classes, right? Whether they are deeper neural networks or deeper decision trees. The more complex they are, the less bias they will have, which means that they can actually learn a lot of things and they will give you really low training error, but they will also have high variance, which means slight changes of the training data will give you large differences. And so for the purposes, so there's going to be a spectrum between simple learners and sophisticated learners. And I'm talking about the endpoints of the spectrum, right? Because I can, obviously with things like neural networks, I can cover that, I can span that spectrum by adding more and more layers in the neural network. With decision trees, with the depth of the decision tree, I can also span that spectrum. But simple learners are going to have low variance. So a linear classifier, if you subsample your data, is not going to change a lot. Right? Because it has very few parameters that it has to learn. It doesn't need a lot of training data. So linear sort of simple methods will have low variance, and they're not usually going to overfit, but they have high bias, and they will not be able to learn really difficult learning problems. So if the concept that you're trying to learn requires a nonlinear decision model, simple methods won't be able to do it. Sophisticated learners like kernel SVMs, deep neural networks, and decision trees, they will have low bias but high variance. Right? So these are two ends of the spectrum and they have opposite problems. And what you'd like is to combine both of these. Ideally, I'd like to have a method that can learn a lot of concepts and requires small amount of training data. So I want ideally low bias and low variance. Right? In general, you can't have that. But what we're going to do is we're going to talk about in certain special cases you can get some improvements. You can try to get good properties of both of these, combine good properties of both types of models. Does that make sense? And that's where voting methods or ensemble methods come in. And the idea is going to be that instead of learning a single classifier, we will learn an ensemble or a community of classifiers. And the output is going to be the weighted vote of each classifier. So, and what we're going to do is we're going to have two types of ensemble methods. One is with sophisticated or complex learners, where if we can assume that we have uncorrelated errors, and we'll talk about this, then we'll try to reduce their variance. So by learning multiple decision trees and averaging their predictions, what you're trying to do is each one of them has a lot of variance, and by averaging, you're trying to reduce their variance. That's one way, and that's going to be bagging. So bagging is a method. So bagging and boosting are both ensemble learning techniques. One of them is used to reduce the variance in high variance classifiers, so sophisticated learners. The other one is called boosting, which is usually used with a weak learner. So you start with a weak learner which has high bias but low variance, and you try to combine them so that you get a low bias, low variance classifier.
What if you combine both?
Yes, what if you try to boost a bagged classifier or bagged a boosted classifier? Yes. Yeah. There's the whole inception argument to anything that I introduce you can repeat 10 times. But let's try to study them separately for now. And yes, obviously you can try to combine these. Here's what's going to happen. I'm going to show you when this is going to work, and I'm going to make a certain assumption, which is when it's going to work, and that assumption will no longer be satisfied after you try to do all these tricks. Right? So the less that assumption is satisfied, the less you can hope to make this work. Does that make sense? Okay. So in your head, you should think about, before I tell you what bagging or boosting is, you should always keep in mind they're useful in two completely different scenarios. You want to bag, and I'll tell you what that is, or average sophisticated learners. Decision trees, neural networks, or kernel SVMs. You do not want to average the predictions of a linear SVM, for example. Right? It's already not overfitting in most cases, unless you have a lot of dimensions, in which case, of course, it's possible. Boosting is used with weak learners. You do not want to do boosting on deep neural networks. There's no point. That's the exact opposite of what you're trying to do. You want to start with a weak learner that has low variance. Okay. So let's go to the first one. And this is the idea of bagging, which stands for bootstrap averaging. Anybody want to tell me what bootstrapping is? It's a concept from statistics. Have you heard of that?
Yeah, bootstrapping for some software, like you start your computer. So it's like bootstrap something, and then this system will automatically run itself, something like that.
Yeah, so that's one concept of bootstrap, and it's not the statistics concept of bootstrap.
That's in computer systems.
Yeah, so the concept of bootstrap, so bagging is equal to bootstrap averaging. The concept of bootstrapping is the idea of resampling a sample data set to create more samples, if that makes sense. So here's let me we have a data set, right? It's x1, y1, all the way till xn, y. think about the set of numbers 1 through n. What we're going to do in bootstrap sampling is we're going to sample from this set of numbers 1 through n with replacement. Right? So you sample n numbers with replacement. The first one might be 10, then it might be 3, then it might be 10 again, right? It's with replacement, and you sample n numbers. You may not see all the numbers. You may see some numbers multiple times. You may, I'm sorry?
Randomly?
Yeah, uniformly with replacement. You may, in the rarest of cases, you may see 1, 1, 1, 1, 1, 1, 1 n times. Right? The probability of that happening is extremely small, but it's possible. And what we're going to do is we're going to create n such data sets. We're going to create 1 data set, 2 data set, m such data sets, each of size n. And we're going to train our classifiers on each such data set. Right? So you have a data set, it has n points. You create new data sets by resampling your points. Right? So some data points get duplicated or triplicated, some data points get dropped, and you have multiple such data sets, they all have size n. You learn your classifier on each one of those, and then you average their predictions at test time. Does that make sense? So you get a Y committee, if you will. If you're doing regression, then you end up doing sort of n equals 1 to n, y hat of n. So x is your input, each one of your classifiers gives you something, then you just average them. This is for regression.
So the repeated data point doesn't really change anything for regression. So why repeat the
The repeat data point does change something for regression. Because another way of thinking about this is instead of thinking of this as repeated data points, you could think of this as assigning a weight here, W1 all the way till Wn. And this weight is an integer going 0 through however many times it was sampled. So if I sample it twice, this weight becomes 2, right? So this is a weight associated with each of your training data. So if you weigh your one data point 1,000 times more than the other, then it's 1,000 times more important, right? It will affect the performance of any such method. That make sense?
That's only for certain methods, right? Like maybe for K-man it makes sense, but not for.
Yeah, so for SVM type things, if one is on the margin, then 1,000 times it's going to be on the margin. Yeah. So there are going to be certain of these outliers where it's not going to make a difference, but in most cases it's going to make a difference. That make sense? Okay, so you learn model 1 all the way till model n, and this is at test time, right? So you make a prediction. And this is your committee prediction. And what we're going to do is we're going to talk about the expected error that this committee makes. So each one of these models has some error that it's making, and we're going to say that by averaging, you actually do better. Not just a little bit better. What we're going to say is that, so this is expected loss type argument, right? So expected loss. So this is the same, if you remember, x and y are sampled from some distribution. The argument that I'll make is that the expected loss, so there's some loss function of y comma y hat committee, x. The expected loss of this is actually equal to 1 over m of summation of n equals 1 to So if each one of these is expected to make some error, if you average that and then divide it by another 1 over m factor, that's going to be the error of this committee method. It's sort of saying that if each one of these things, notice that there's an m squared effect happening. The average already has 1 over m sitting inside it. Right? I'm saying that if there are 10 of these things that you learn, on average, let's say they're making 20% error, there's another 1/10 factor that you gain if certain assumptions are true. That make sense? This is what this is a short. I think we can do that. Yeah, this is a short proof that we do. That makes sense. Do people understand the statement of that's what we're trying to do?
I don't understand.
So we're going to learn a committee of classifiers, right? Forget the expected bit, right? Each one of them makes some error on a data set. Let's say you average that error, and let's say the average is 20%. On average, they're making 20% error. This one is making 25, that one's making 15, on average 20. You divide by another factor of m, and that's the error that this committee is making. So somehow by averaging the predictions, you do better than the average of the errors, and better by a factor of m, 1 over m. So if you have a really large committee, you can drive down the error to 0, but this is going to be under certain assumptions, which will not be possible if you have a really large committee. Does that make sense? Okay. Here's how we're going to do this. So let's see. I'm going to make my life easy, and I'm going to assume we're talking about regression and L2 loss. But this is L2 loss. So expected. So assume regression and L2 loss. Squared error, right? So this is expected value of y ground truth minus 1 over m summation of ym squared. Right? That's the quantity that we're interested in. That's that left-hand side. Loss is squared loss of the committee. And what I'm going to do is I'm going to say this is expected value of 1 over m squared of m times y minus summation of ym. Okay. So far, just taken an m out. Linearity of expectation. So not linearity of expectation, but constants sort of step out. So I can write this. Let me not write too much. Okay. So I can write this 1 over m squared outside. I can do this. That makes sense? Okay. I'm also going to make my life a little easier. I'm going to say y minus ym. I'm going to say this is error of the nth model. Right? And so if you stare at this summation, this is basically equal to 1 over m squared expected value of summation of em squared. M equals 1 through. Okay. That makes sense. Okay. Everybody's waiting for where the kicker is coming in. So it's a summation of terms squared. So we know that there is going to be a. So I'm going to write the expected value there. I keep forgetting that. So there's summation of em squared. M equals 1 through m plus all the cross terms. M1 not equal to M2, E M1 times E M2. Right? I just opened this, so expectation is still sitting outside. It was a summation of a bunch of errors, the whole squared, which is equal to summation of squared plus summation of the cross terms. Right? So A1 plus A2 squared is A1 squared. Oh, well, I don't need a 2. I'm fine. So A1 plus A2 squared is A1 squared plus A2 squared plus 2 A1 A2, which is the same as A1 times A2, A2 times A1. This is all the cross terms. Okay, and this is the place where I'll make 2 assumptions. One of them will be perfectly fine. It'll be like an easy assumption. The other one will be things that you should argue that this is BS. Why should this be true? And you'll have to tell me which one is which. Okay, so here's assumption number 1. So this is my assumption. Assumption number 1, I assume that on average the errors are 0, right? So I assume expected value of EM is actually equal to 0. So this is unbiased errors, right? So like on average, my predictor is 0 error, and the other is uncorrelated errors. Uncorrelated errors. And this is saying that the error that M1 makes does not tell me anything about the error that M2 makes. So this is expected value of EM1 times expected value of EM2. So I train M classifiers, or M regressors in this case. This one makes an error, this one makes an error, and this one's error does not actually tell me anything about that one. So the expected value of the product is expected value of this times expected value of this. Two assumptions. What?
The second one makes sense. somehow.
Second one makes sense. The first one does not. Anyone disagree with that? You disagree. Yeah.
Second one can be correlated because we are taking from the same data.
Taking the same data. So
Not
let's
technically
do
the same data.
what?
Not technically the same data.
No, yeah, there's like different samplings of the data, right? So let me tell you, like once you make these two assumptions, there's like 2 lines to get to where I want. So let me do that, and then I'll leave you to ponder which one is true. So all I have to do is, now that I've made the 2 assumptions, I just have to apply linearity of expectation. Right? This is expectation of this plus expectation of this. So it's 1 over m squared. Now it's expectation, summation m going 1 through m, expected value of em squared, right? Em squared expected value. Okay. I have to do that. And then there's a second, so expected value of this, which factorizes into expected value of those two. Each one of those factors is 0, so this term just goes away. That's where the magic comes in. Right? The products factorize, because I assume they were uncorrelated, they were also 0 mean, and therefore that term goes away. So that's the only term I'm left with. 1 over m squared, summation of expected error squared. And what is expected error squared? That's expected value of y minus y hat of m squared, right? And so I get 1 over, so there's a summation here, m equals 1 through m, and 1 over m squared, which is equal to 1 over m times the average value. That's what I started out to prove. So you somehow take each one of the committee, their expected error, and there's a 1 over m that goes into the average, and you still cut that by 1 over m. Okay, so this is just logic, right? You can't argue against this. I made certain assumptions, so I can start from A and get to B. That anybody can do. But what does this mean? What's happening here is somehow there were a bunch of terms that now don't exist because of this. Right? That's why you're getting, there's an extra m happening here. That magic is coming because I'm assuming these terms go to 0. Turns out that if I let you in on the secret, this assumption is perfectly fine. Zero mean or unbiased errors are perfectly fine. Because if this was not 0, think of a linear regressor that is on average off by 2. Right? Then it just means that you just need to shift the average down. Like you just need to add a bias term to that, right? If this was some non-zero term, then it does not depend on x, then you can shift it down. It would have learned that. That's very easy to fix. It's this that's sort of problematic. If it's true, then the results are awesome. If it is true that you can learn a committee of classifiers where the errors made on one do not tell you anything about the errors made on the other one, then a whole bunch of these terms go away, and by averaging their predictions, you suddenly do a lot better. It's because the errors that were being made here are uncorrelated with the errors that were made here, so the averages are better than everything that you're averaging. Right? Noise goes away once you average those things. What's going to be hard is this actually ever true? Right? So if you take a data set and you resample it multiple times, it's unlikely that this is going to be true. We can never actually guarantee it. We can hope for it. The way we try to do this is we try to make each one of those predictors as diverse as possible. learn on a different subset of data, learn on a different subset of features. If you can make the errors uncorrelated, then you suddenly get these gains. Right? And that's where bootstrap sampling comes in. That's one way of achieving that, but there are other ways of achieving. Ultimately, what you want is this. If this is satisfied, then we're home free. We got this sort of 1 over extra m factor. Does that make sense? Okay, let me stop here.